Okay, so today's quiz is canceled. So we'll just keep going with this topic. We're almost done with all the stuff, so you can do all the problems in Newton's second law and free body diagrams. So last time we started talking about friction, and so we said there's two types of friction: the static friction that holds something at rest, and kinetic friction that acts when something's sliding. It's the thing that if something's sliding along a flat surface, it won't slide forever. That's because of friction. So there's static friction, and we're not doing that one. And we are doing kinetic friction, so that's the friction when something's sliding. So for kinetic friction, the direction is always opposite the velocity vector. And that's why in all of these friction problems, I'm going to have to tell you which way the object is sliding at the instant that we're analyzing. We haven't ever had to do that before because Newton's second law deals with accelerations. But now we have something, this friction force, whose, its direction depends on what we know about the velocity vector. What if there's no velocity vector? Then there's no then there might be static friction, but it's not the kind that we're doing. So the friction problems that we're doing, there always has to be a velocity vector. It always has to be sliding. And then the magnitude F sub F, so the force of friction, is equal to this constant mu, and it always has a sub k because there's also this constant also is the same way you deal with static friction, and there's a different one for that. And then times the normal force. And this normal force is the contact force between the thing that's sliding, the object that's sliding, and the surface it's sliding across. We spell across, not like that. And then, okay, so let's do a really simple friction problem. And then after that, I'm going to remind you of the really bad news about these friction problems. You were trying to forget it, but you can't. Okay, so let's say there's a box sliding across the floor. And the box has a mass of 20 kilograms. And the box is sliding this way, so that's the direction of the velocity vector. And there's a force applied to the box pushing it this way, where this angle is 30 degrees. And the magnitude of this force is 80 newtons. Okay, so first let's try to make sense out of what's going on here. There's a lot of stuff in this picture. So my first question is, well, so it says there's a force going that way, right? There's a gravity force, there's a contact force, and then there's another force pushing it that way. So those will be all the forces. The thing is sliding this direction, which is opposite the horizontal part of that 80 Newton force. So first, how can this picture even make sense? You know, that's I think the first thing you have to sort of understand with these problems, because we haven't dealt with velocity before. Like, you look at this and you're like, that 80 Newton force is never going to make it go this way, right? So is this possible? Yep. Yeah, that's exactly right. So the thing is, think of the velocity as something that's built up from all the forces that have been applied in the past, okay? So as far as we know, right up until this instant, there was a big force pushing it this way, and it got moving really fast. And then once it's moving really fast, then that force disappears and you apply this one. Well, that one will help slow it down, but there's nothing incompatible about those two things. You know what I mean? So think of this as, that's old news. That comes from what happened before. This is the current stuff, okay? But the direction of that friction force depends on this velocity, which depends on that old news, okay? So yes, those don't have to, the forces that are shown there don't have to make the thing slide in the direction of the velocity. That comes from the past. Okay, so what's the first step? Yep. That's always a good thing to say. Even if it doesn't have anything to do with the problem, it's somehow like it's still, I just like to hear people say it. Sure, it can't hurt. Why not? No. No, do it. Yeah. Do it in your car, whenever. It never hurts to draw a free body diagram. In a car, it does hurt. That's right. That's true. In physics, it never hurts. Yes, in the car, I guess, yes, it's a really bad idea. Okay, so there's the weight. 20 kilograms times 9.81 is 196.2, right? Yes. And then there's a contact force from the ground. Then there's a friction force from the ground. Which way does that go? Opposite of velocity, so I'll draw it over here like this. And I didn't give you. But let's say the coefficient is basically always going to be given. Let's say that the coefficient of kinetic friction is equal to 0.1. Okay. Oh, what are the units? I didn't say that. What are the units of the coefficient of friction? How can you tell? You can tell from the equation for the magnitude, because what are the units of the force of friction? Newtons, that's a force. And what are the units of the normal force? Newtons. And so if this thing times newtons is equal to newtons, what are the units of that? It's just a number. If it was newtons, it would be newton squared. So this just has to be a pure number. You can always figure out the units of any coefficient in any equation that way. Like, what if you didn't remember the units of the universal gas constant, I'm going to put this down here, erase it later. Okay, so P. How are you used to doing it? With a true volume? So like this, let's do it like this. nRT. Okay, that works, right? What? Oh, yeah. So what if someone asked you the units of this universal gas constant, and all you remember is it's 8.314? Well, with any any science equation, the units have to work out. So if you know that the pressure is in newtons per meter squared, and the volume is in meters cubed, and N is in moles, and then you have your R that you're trying to find the units of, and then your temperature is in Kelvin. Then divide these over the other side. I guess let's cancel some of these first. So those go away. You have 1 meter left on top. Divide these over, and you get that Newton meters divided by moles times Kelvin are the units for the universal gas constant. So you can always manipulate any equation like that to figure out the units of anything you want. So what I was saying before was, if you know this equation, force of friction is equal to the coefficient times the normal force. So that says newtons is equal to this coefficient times newtons. So divide both sides by newtons, and you get that this coefficient is equal to, you know, newtons over newtons, which is, the units cancel out. It's just a pure number. I just like to put chemistry in sometimes to trick you guys into thinking that you should listen. Like, oh, what was that? Moles? Okay, so we're still on this free body diagram. So we know the direction is to the right. We know the magnitude is the coefficient, 0.1, times the normal force. So I'll just write that in like that. And then we have this force that has a magnitude of, what did I say, 80? Yes. And that's all the forces. You know, what we did was we put the weight force in there, and then we just went around looking for contact with the surroundings. There was contact up here, so we put that in. There was contact at the ground, so we put in a normal force, and then we know it's a friction problem, so we put in the friction, and then that's it. So now, before we do Newton's second law, we have to deal with the fact that this 80 Newton force is in an angle. So I'll call this vector, you know, the force of that 80 Newton force. So how do I calculate that in components? Exactly. 80 times cosine of negative 30. Yep, 80 times sine of negative 30. This one is negative 40. Can someone calculate 80 times cosine of negative 30? Yeah, so whenever I don't draw an axis, we'll just assume that it's the usual one. Yes, that's right. So when you're doing these friction problems, that's what I was going to talk about after this, but you put the y-axis pointing out of the surface. So in this case, the normal coordinate system is the one that you would use. $69.28. Okay, so now we'll go to Newton's second law. So we have 0, negative 196.2. plus 0n. The 0.1n is in the positive x direction, so plus 1n 0. Plus 69.28 negative 40 is equal to mass 20. And then what do we know about the acceleration? So what you're always trying to determine in these problems is, we know that it's only going to move along the x-axis or only move along the y-axis. In this case, it'll move along the x-axis. And besides that, we don't have to think about the sign or anything. The math will give us the sign. So I'm just going to write this as A0. Okay, so the x equation says 0.1n plus 69.28 is equal to 20a. And the y-axis, the y equation says negative 196.2 plus n minus 40 is equal to 0. In problems without friction, remember we've done a bunch of examples where we've just thrown away one of these equations. They didn't do us any good. And so normally, like in this case, if we're trying to calculate the acceleration, if there was no friction, the only one that would be useful would be the x equation. But now we need to use both of them every time. And the reason we need the y equation is because there's an n in here, and we have to use the y equation to find n before we plug it in. And so that's just always going to be the approach. Use the y equation to find n, plug n into here, and solve for a. It's two equations for two variables. So the y equation says n is equal to 236.2 newtons. And now plug that into the x equation. And the x equation says 0.1 times 236.2 plus 69.28 is equal to 20a. So 23.62 plus 69.28 is equal to 20a. So that's 92.9. So 92.90 is equal to 20a. And so A is equal to 46.45. 4.645. Damn it. Any questions about that? Okay, so the acceleration is in the, well, let's get the vector. Okay, that's just the variable. So the acceleration vector is what you get if you plug that back into A from Newton's second law. And so you get 4.645 Or in other words, what direction is that pointing? Left or right? Right. So the other way to think of it is a vector with a magnitude of 4.645. Okay, so The acceleration is to the right. The velocity is to the left. So is that box speeding up or slowing down? Slowing down because they have the opposite directions. So now let's think about what would happen if everything's the same here and we switch the direction of v. Okay. So what's going to change in the free body diagram? Yeah, only one thing is going to change in the free body diagram if we switch the direction it's sliding. And this will switch directions too because it's always opposite. And we'll go through the calculations. But think about this. What if there was no friction on this? So this was on ice or something, and we're assuming there's no friction. Does it matter if we're trying to calculate the acceleration? Is there anything that changes the acceleration, like say that it's at rest or moving to the left or moving to the right? Is there anything about any of those velocities that would change the answer we would get for acceleration? In the case of no friction, there isn't. And so you might, if they're on these problems without friction, you might sort of think like, assume that it's at rest. But the truth is, it doesn't matter whether it's at rest or not. Your answer for acceleration would be the same whether it was moving this way or that way or stopped. But with friction, that's not true anymore. Okay? Any questions about that? So, okay, so let's just think, let me just try to explain this one more time. So say that there's no friction there, okay? And say that you just have a horizontal 50 Newton force, let's say 60 Newton force, pushing this to the right, okay? Well, that would be the only horizontal force, and so the x component of Newton's second law would tell us that the acceleration is equal to 3 meters per second squared going that way. Okay? And that answer didn't depend at all on the velocity because there's nothing about any of those forces that depends on the velocity. So that would be true whether that block was moving 10 miles per hour that way or 10 miles per hour that way or stopped. You know, if it was moving, I'm going to stop there. Okay, but so here's the take-home message that I'm trying to get to is if you're not dealing with friction, the velocity doesn't change anything. If you are dealing with friction, the velocity changes your answers for forces and accelerations and everything. Okay. Okay, so now we'll do it the same as above. Now the velocity vector is this way. A free body diagram. There's the weight force of 196.2. There's the pushing force, the normal force from the ground. And then there is the friction force that's opposite the velocity, so this way. And how do I label this? 0.1 N. Yep. Can you guys all try to be a little more like Tyler, please? I just call it like I see it. Okay, so well, net force is 80 newtons. Okay, so Newton's second law says 0, negative 196.2 plus 0n plus, so what are the components of 0.1n now? Yeah, now that's in the negative x direction, so negative 0.1n 0. And then that force, the components are still the same, so that's 69.28 negative 40. Mm-hmm. Yes, and you know, on these, yeah, so this is, a lot of times if we're using this usual coordinate system, I guess it's sort of sloppy, I just don't even write it up there. But yeah, all of this is based on assuming that we're using a positive x-axis to the right and y up.
So now I'm confused on how we determine acceleration.
We did not have to know that. We just, all we have to do when we're writing down the acceleration is decide whether it is free to move along the x-axis or along the y-axis. And we don't have to think about whether it's positive or negative. That'll come out in the math. So in this one, you know, in the last one, it was sort of easy to, if you had to decide what direction it was going to move, accelerate, you could tell that it would be in the x-axis because all the horizontal forces were in the positive x-axis. In this one, there's one going each way, and so there's no real way to eyeball it. It just ends up depending which of these components is bigger. That doesn't matter, though, because we're still going to write that acceleration just as A0 and let it come out in the math. Maybe we'll get a negative answer. So 20 times A0. Okay, so the x equation says negative 0.1 n plus 69.28 is equal to 20a. And the y equation says negative 196.2 plus n minus 40 is equal to 0. Okay, so how do we go about solving this? Solve for n with the y equation and then plug it into x. Yep, I think that's every single friction problem. That's the way that you're going to do it. So n up being what it was last time, 236.2. And then the x equation says negative 0.1 times 236.2 plus 69.28 is equal to 20a. Question? No. So now we have negative 23.62 plus 69.28 is equal to 20a. Can someone calculate that for me? So A is 45.66 meters per second squared. And so the acceleration vector is, you know, now plug that back into, like if, Yes? What? Oh, that's what, yeah. So that's 20A. So A is equal to what, 2.2? Okay, 2.28 meters per second squared. And now plug that back into the acceleration vector from Newton's second law. And you get 2.280. Meters per second squared, or that's in the positive x direction again. So you could also think of it as a vector to the right with a magnitude of 2.28. So in this case, is the box speeding up or slowing down? Yeah, so now the acceleration's in the same direction as velocity, so it's speeding up. What changed was, well, the magnitude of the acceleration went down a lot from the first case to the second case. And the reason for that is the friction force, no matter what the other forces are doing, the friction force is always trying to slow the object down. Okay, that's all friction can do. There's no way to manipulate friction so that it can make something take off. It's always just slowing things down. And so in this case, instead of working with that 80 Newton force to slow the object down, the 80 Newton force was trying to speed it up and the friction was trying to fight against it to slow it down. Any questions about that? Okay. So now, I also said last time for any sliding or rolling problem, choose a y-axis directly out of the surface. So, for example, if your surface is like that, your y-axis would be perpendicular to it like this. And then the x-axis can only be this way because coordinate systems have to be rotated versions of the normal one. It can't be flipped versions. So if you did the y-axis like this and then put the x-axis down, that would be taking that original coordinate system and flipping it before you rotate it. Well, notice that in the examples we just did, in any problem where the thing is sliding along a horizontal surface, that's how the usual coordinate system works. The y-axis points out of the surface. So it's only on inclined ones or ones sliding along the wall or being pushed along a ceiling or something where you have to rotate the coordinate system from what we're used to. Okay, so when you do that, here's what is always the same. The acceleration vector, you can just always represent as A0, because the thing can only, if the thing's sliding and your x-axis is always along the surface, then the acceleration has to be along the x-axis. It'll sometimes come out to be negative, but that'll come out in the math. So you can always just start like this. The normal force will always be 0n, because it's always pointing out of the surface, and that's the same thing that we're doing with y. And the friction force this one can be positive or negative, and so you have to choose that depending on the problem, but it'll always be plus or minus the coefficient times the normal force for the x component, and then 0 for the y component. Okay, so let me do one where an object's sliding down an incline. So let's say this angle is 20 degrees. The box is 10 kilograms. And it's sliding down, so this is the direction of motion, the direction of the velocity vector. And the only external force on this is a perpendicular force like that. And let's say it's 100 newtons. So start, what? Oh, one again. I'm not very creative with those. So free body diagram. I just had this thought that we could calculate those in lab. That'd be sort of cool. Calculate coefficients of friction. Like we could push like each person across the floor one by one and see who has the highest coefficient of friction. Wear your leather pants that day. Okay, so there's a weight force. I didn't show the coordinate system, but what would the coordinate system be? The y-axis has to be directly out of the surface, the incline. So that's the y-axis, and so then the x-axis has to be like that. And these problems, I'm not going to draw the coordinate system on there. You have to choose that yourself. Okay, so the weight force is 98.1. There's a force of 100 newtons, like that. There's a normal force perpendicular to the surface toward the chosen body, so that way. And the friction force is opposite the direction of motion, so it's this way. and it doesn't matter where you draw it. Right now, we're still treating everything as a particle. So no matter where I draw it, everything's really happening at a single point as far as we're concerned. So just draw it wherever the picture looks less cluttered. So 0.1 n. And now we have to figure out what the components of these vectors are. So I'll call this Fn, the normal force. That's what I said above, it always is, 0n. So that's great, it's easy. The friction force, is that in the positive or negative x direction? Positive. So that's, I'll call that force of friction vector is equal to positive 0.1 n 0. 100 Newton force. That happens to be exactly in line with our y-axis. It's in the direction of negative y. So that's going to be 0, negative 100. And the acceleration is what it always is. We'll just start with it as a0 and calculate what a is. But now we get to the one thing that we've made more complicated by rotating the coordinate system. We have to calculate that weight force. And the weight has always been like our easiest warm-up starting point, you know? But now it's the one thing that we have to do the trigonometry to solve. But this is just like the vector problems that you did in, you know, the vector practice problems. So we have a vector with a magnitude of 98. And the x-axis is this way. The y-axis is this way. And the horizontal is this. So the x-axis makes that 20-degree angle with the horizontal. If this angle is 20 degrees between the horizontal and the x, this angle has to be 20 degrees between the vertical and the negative y. Do you see that? If we took this thing that's made out of 90-degree angles, you know, and we still, so what I'm talking about is, imagine starting the coordinate system in its normal orientation, and then we just tilted the whole thing 20 degrees like that. And so the x-axis is 20 degrees off the horizontal, and the y-axis is 20 degrees off the vertical. So all of these angles, if I drew all these verticals and all these horizontals, this is now 20, this is now 20. But the one we care about is the one we care about is this, because what we're trying to do is figure out the angle to get from the positive x-axis to the weight force vector. Remember, that's how you calculate vector components in in any coordinate system. But so if you go all the way from the x-axis around to this y-axis, that would be 270. But we didn't quite make it there, so backtrack 20. And so the angle is 250 degrees. You see that? Or anybody have any questions about that? If you go back and look at those vector practice problems, you'll see that this is just, exactly that same kind of thing. And you're always just going to be having to figure out the angle between your new negative y-axis and that downward vertical line. Okay, so theta is equal to 250. And so the weight force, I'll call it mg vector, is equal to 98.1 times the cosine of 250 98.1 times the sine of 250. And can someone calculate? Oh, I have that here. Do I? That's negative 33.55, negative 92.18. Looking at that picture, does it make sense that both of those components are negative? Yeah, because our coordinate system is the green one, and the vector that we're describing is in that coordinate system's third quadrant. So they do both have to be. Okay, so now we can finally put this all together in Newton's second law. So we have 0n plus 0.1n 0 plus 0 negative 100 plus negative 33.55 negative 92.18 is equal to the mass, 10 kilograms, times the acceleration. So the normal force is equal to, I'm using the y equation, the normal force is equal to 192.18. And then plug that into the x equation, and you get 0.1 times 192.18 minus 33.55 is equal to 10a. So 19.22 minus 33.55 is equal to 10a. Can someone calculate a? Negative 1.43 meters per second squared. And so plug that back into the acceleration vector, and you get that the acceleration vector is negative 1.430, or it's in the negative x direction. Now our negative x direction is tilted along that new coordinate system, so it's like this direction. Magnitude of 1.43 meters per second squared. So is this box speeding up or slowing down? Speeding up because it was originally moving down the ramp, and if the velocity and acceleration are both down, then it's speeding up down the ramp. Okay, so I have a question here. looking at this, do you think that 100 Newton force does anything? Because what we're doing, we're calculating an acceleration that's perpendicular to it. So that's not trying to push it up the ramp or push it down the ramp. Do you think that has any effect on the acceleration? I mean, you could go back to the equations and see whether that 100 comes in anything that calculates the acceleration. But I just sort of want you to have kind of an intuitive idea of how this works. What if there was no friction? So get rid of that. Do you think that 100 Newton force would have any effect on the acceleration? In that case, it would not. If there was no friction, you could put as much force vertically as you want, and the acceleration would still be the same. And that's, you know, like when we do problems like this without friction, we skip the y equation altogether and just use the x equation. And so that would never even come into it. With friction, it does affect the answer. And the reason is that 100 Newton force increases the normal force. You see that? Like if you're mashing, so right now, this tape has a small normal force with the table. But if I do this, the normal force that the table has to apply to keep it from accelerating down gets bigger, you know? And so that's what this is doing, mashing it down into the incline. And when you mash those things together, it increases the friction force. You know, and I mean, that's totally like, makes sense to you. Like, is it easier to slide this along the table now, or if I put all my weight on it? You know, that makes it a lot harder. So a vertical force like that increases the normal force, which increases the friction force. Okay, let me give you one to do. So let's say this angle is 10 degrees. And this box is 2 kilograms and it's sliding down. If the coefficient of friction, kinetic friction, is 0.2, what's the acceleration vector? Okay, so go ahead, ask me questions if you get time. Okay, so the coordinate system is like this. The y-axis is there. The x-axis is here. Free body diagram. Uh, 19.62 is the weight. There's the normal. Friction is up the ramp. Yeah, well, I just draw it in the direction it is and put the number positive, I think is the best way to do it. It is in the negative x direction, yeah. No, so you could, if you wanted, draw it in this direction and write the number negative, but don't do both of them because then that's like a double negative and it switches it back, you know? Okay, so acceleration, normal, friction, those are all easy to come up with those vectors. But the weight force, the magnitude is 19.62. The red is the horizontal. and vertical. Okay, so this angle is 10 degrees. And so is this angle. And this one, and this one. Mm-hmm. Okay, so the original, like the horizontal and vertical are the red dotted lines. Okay. And then we imagine starting with the coordinate system in the normal position and then tilting it 10 degrees like that. Okay, so now all of our new axes make 10-degree angles with the verticals and horizontals.
Could you not draw it with the red? Like you just draw it with the normal coordinate system. You do the red thing and add the 10 degrees. That just
Okay,
messes it up.
right now?
Yeah,
Sure.
please.
He lost my tilting it. All that.
Okay, that makes more sense.
I don't like it. Change it back. That's what no, that didn't help. Can you change it back? But I mean, the basic idea is like, think of that green thing as like a physical structure, you know, like it's a rigid thing that you can turn, you know, and its usual position is lined up right with these black lines. And then we just took the whole thing and tilted it 10 degrees like that. Because we needed the coordinate system to have the y-axis pointing out of the incline. We needed it to match this.
It's because the object is slanted.
Yeah,
so you
it
have
has to match the incline.
No,
In this original picture, the y-axis has to point directly out of the incline. And so to do that, we had to start with it in the black position and then rotate it 10 degrees. So now this green one matches this green one.
the dotted line is the original.
Yeah. Yeah, think of the dotted line as where the green one started before we tilted it. Okay, so yes.
So when we're making practices like that,
Okay. Again.
Yes. Yes, that's right. Exactly. Yeah, so the angle we're always looking for is this angle between the negative vertical, the downward vertical, and the negative y-axis. Okay, so now the last thing we have to do is figure out the angle. So what we're trying to do is go from the positive x-axis counterclockwise to the vector. So from the positive x-axis, it's 270 to this green line, and then another 10 to get to the gravity, the weight force. And so you get theta of 280. And so that weight force is equal to 19.62 times cosine of 280, 19.62 times sine of 280. Can someone calculate those? Does it make sense that the x component's positive and the y is negative? Yep, it's in the fourth quadrant. round off air. Okay, so Newton's second law says 0n plus negative 0.2n 0 plus 3.41 negative 19.32 is equal to the mass, what was it, 2? Times the acceleration. The y equation says the normal force is equal to 19.32. And the x equation says negative 0.2 times 19.32 plus 3.41 is equal to 2a. Can someone calculate a? $3.867.27 divided by 2. 3. Negative 0.227. And plug that back into the acceleration vector, and you get an acceleration of negative 0.2270, or that's in the direction, the negative x direction. So this way with a magnitude of 0.227. So is it speeding up or slowing down? It's slowing down, but very little. That's a very small acceleration. Basically, like gravity is trying to make it speed up down the ramp. Friction's trying to make it slow down. They sort of counteract each other, and this thing is moving almost with a constant velocity, but slowing down a little bit. Any questions about that? Okay, that's it. So, I didn't say this at the beginning of class, but the test is postponed, right?
Yeah.
That was on D2L. I thought for a second I thought that was my other class. Okay, so